Thank you everyone for coming to the Jones seminar today. We're really excited to have Sinead Farrell here to talk about exploring Arctic sea ice with NASA ISAT-2. Sinead did her PhD at the University College London in space and climate physics. She studies cryospheric science and remote sensing with a focus on sea ice. She's part of the NASA ISAT-2 science team and of the mission advisory group for the Copernicus Polar Ice and Snow Topography Altimeter. She works on altimetry. And yeah, we're really excited to hear what she's going to say today. And so thank you for joining us. Take it away, Sinead.
Well, good afternoon, everybody. It's Friday afternoon, yay. We've made it through the week. I hope this ends up being a kind of relaxing mental health break for most people. It's not a topic I guess folks are super familiar with. So I'm delighted to be here. Thank you very much for inviting me to participate in the Jones seminar. I appreciate that. Delighted to speak with you today. So yeah, as Colin said, my name is Sinead Farrell, and I run the Polar Oceans Laser and Radar Altimetry group at the University of Maryland. And really what we're focused on is looking at changes in the Arctic sea ice, really to understand changes in the thickness and the volume of the sea ice. In particular. My background is in remote sensing. So my training, it was a combination of geophysics and remote sensing as an undergraduate and graduate student in the University College London. And we're really looking to advance remote sensing techniques specifically for measuring sea ice. I mostly focused on the Arctic, but we're interested in all types of sea ice, both in the Arctic and Antarctic. And we're using not only satellite altimetry, but also synthetic aperture radar, SAR, optical imagery, and other types of remote sensing measurements. So another aspect of the work that we do is, of course, calibrating and validating our work. So we're engaged with activities either by aircraft or in the field, in situ measurements. So basically activities that obtain independent observations of the sea ice cover. And we use those to understand the quality of the satellite measurements and the observations that we're making. So today we're going to be talking about remote sensing of the Arctic Ocean, specifically focused on sea ice, which is simply the frozen ocean. And really going to talk about what we're learning from NASA's ISAT-2 mission, which was a mission launched just about 2 years ago now. So if anybody has questions for me, I'm happy to take those during the session. I'm probably not going to be able to see the chat. But you know, we can do a Q&A where we've got time for a Q&A at the end, but don't hesitate to stop me if you're having trouble hearing me, understanding what I'm saying. I'm really amenable to questions. So, you know, please feel free to butt in if needs be. So without further ado, I'll just jump into it. So as you probably are aware, maybe not this week, but sea ice tends to be in the news a lot, particularly the Arctic ice cover. I think it's pretty well known at this point that it's in decline. And this year in particular, I just chose one headline here from the Guardian newspaper stating that we had reached the second lowest level of sea ice in the summertime over 40 years, over our 40-year record. Now, the record that we're talking about here is a satellite record. So measurements of the ice area obtained by passive microwave radiometers on satellites that are orbiting the Earth. So if you look at the map on the left-hand side, we're looking at a kind of, it's a cartoon map really, of the ice extent in summertime. And obviously in the summer, that's when we reach our minimum extent each year. It's an annual cycle of growth and melt. And so we had, the white area indicates the ice extent in 2012. And that was when we hit an all-time record minimum sea ice extent in this 40-year plus satellite record. But this year, this summer 2020, we were pretty close to that minimum, that 2012 minimum. So it was the second lowest level on record. And so the graph on the right-hand side really shows that. What we're looking at here, if you focus first of all on the gray curve, this is the change in ice extent over the course of the year. So it's going from October through to September on the x-axis. And what we're seeing is that the ice actually grows from October through to March, April, and then starts to melt back, okay, decline into the summer period, and it reaches its minimum in September. So this is a natural cycle of growth and decay. It's nothing to do with climate change. And the gray curve is really what we would call the climatology. Again, recorded simply from satellite observations, but this is as best as we have for knowledge of the entire aerial coverage of the Arctic sea ice cover. Now, what has changed due to a warming Arctic is what's been happening in the last sort of 20 years. So the second part of this 40-year time series. So the red curve here, the dashed red curve, is the record 2012 minimum. And then the blue curve is showing you what happened in 2020 this year. So, you know, as I said, September 2020, we were just above the record minimum set in 2012. But what I want to point out is that in April of 2020, we were well below that 2012 curve. So in other words, the deviation here between the blue and the red curves here. And this April 2020 extent, this is actually at the time of sea ice maximum. Okay, this is when the ice is at its full growth and has reached its full extent for the year. And this April 2020, we were about the third or fourth lowest on record again over this 40 years. So this has been a tough year for the sea ice. And if you have been following this, if that's a topic of interest to you, you'll know that there's severe problems right now in the eastern Siberian Sea and the Laptev Sea, in the area basically off of the coast of Russia, where the ice is actually not really reforming yet this winter. So there's a very late freeze up of the sea ice. So why is this happening? Okay. It's a result of a phenomenon called Arctic amplification. So on the left here, I'm just showing a map of global temperature anomalies. And this is from a global model, but it's showing the anomaly in September 2019 relative again to a climatology. And what you can see here are the red areas are the areas that are warming the fastest. And so the Arctic here is warming, it's above about 2 to 4 degrees Celsius above average. And you can sort of see there are some other areas on the planet where this similar levels of warming are occurring, but the Arctic, it's a widespread rather than a regional warming. It's right across this entire Arctic Ocean area. And the reason for this is because of, well, Arctic amplification really is driven by a phenomenon known as the sea ice albedo feedback. So basically you have a very bright surface, a high albedo surface, that is the sea ice, often covered in snow, which makes it even brighter. And as we have increasing global temperatures, this is causing a decrease in the Earth's sea ice cover, and in fact also with the snow cover on land. But this overall decrease in sea ice means that there is an overall decrease in the regional albedo. And that in turn allows the Earth to absorb more of the shortwave radiation. Okay, so more of the incoming sunlight is absorbed. And this is further amplifying warming. Okay, so that and then in turn, that warming further amplifies sea ice melt and causes further retreat. So this is what we know as a positive feedback loop. So I'm sure as members of the engineering school, you're very well aware of feedback loops. So this is really one of the major drivers of Arctic amplification, i.e. the serious sort of rapid decline in the sea ice cover. It's a positive feedback loop. Okay, and as I said, it's not just, you know, the global temperatures are warming, but in the Arctic, we're actually now showing, or we know that the Arctic is warming at about twice the rate of the global average rate, okay? And then it is occurring, the graph on the left is actually a graph of land surface temperature. And on the right-hand side, I'm just showing a map of trends in sea surface temperature. And I think what's really important is that we understand that this warming is not just happening in the atmosphere, but it's also happening in the ocean. And so the real crux of the problem for the Arctic right now is this warming in the Chukchi Sea. This map is a little bit of a strange projection, but the bottom area here where it says Chukchi Sea, this is north of the Bering Strait, okay, between Alaska and Siberia. And north of that is the Chukchi Sea. And this is an area of rapid warming in the Arctic Ocean. And of course, if the ocean is warmer than normal, that inhibits the refreezing of the sea ice. So, you know, a lot of folks are focused on monitoring what's known as the heat blob in the Chukchi Sea. Not a very scientific term, but that seems to be what's been used in the media. So the long-term impacts then of this Arctic amplification are that, of course, the ice has been in decline. And, you know, the graph on the left-hand side is, oh, I'm so sorry. Sorry, I didn't realize that was going to happen. The graph on the left-hand side is showing us again, the ice extent anomalies over time. Okay, so now we're looking at the time series of 40 years from the satellite passive microwave radiometer measurements. And as I mentioned, the sea ice reaches its minimum extent in September every year. And if we look at the trend in September ice extent, we're losing about 13% per decade in terms of the ice extent. But it's not just the summer, right? It's happening in every month of the year. And if we look at that same metric for March, when the sea ice is at its maximum each year, we're still seeing a decline in the extent. Now that's a little bit less, that's at about 3% per decade. And then on the right-hand side, we're also able to measure the age of the ice. The same satellite measurement, the passive microwave, is being used to track individual ice flows here. And so we can look at these ice flows and how they drift across the Arctic Ocean over time. And we can keep track of those and sort of estimate how old they are. And so the maps on the right-hand side are actually contrasting the age of the ice in the number of years between 1985 and 2019. And again, this is in March, so this is at the height of winter. And what you can see is that the red colors that were very prevalent in the 1980s, indicating that the ice was over 4 years old, it persisted, in other words, for 4 years or more. That type of sea ice has really disappeared now. And we're left with ice that is predominantly seasonal. This kind of dark blue color is showing ice that is less than 1 year old. That's the seasonal sea ice. And then the multi-year ice, the ice that's greater than 1 year of age, is much less than what we had in the past. So whereas we had about 35% seasonal ice cover in the 80s, we now have about 70% seasonal sea ice at the height of winter currently. So these are the kind of long-term changes that are occurring. So obviously there's a large range of socioeconomic impacts, not to mention environmental and climate impacts. But I wanted to just sort of explain one, or present you with one a particular socioeconomic impact. And this is to illustrate that the changes that are occurring in the Arctic can be considered either positive or negative. I mean, as an earth scientist, I'm just observing this and presenting this information, not trying to tell you that this is doom and gloom, because actually for some, it is positive, okay? So if you're into shipping cargo, the loss of Arctic sea ice is actually good news. Okay, so this is a little bit cynical of me to say that, but I think you get the point, that there's always an upside to every downside. Okay, so the Northern Sea Route, which is the transportation route around the eastern Arctic, if you like, around the Siberian side of the Arctic Ocean, so around northern Scandinavia and then off the coast of Russia through the Bering Strait to Asia. The Northern Sea Route actually shaves about 2 weeks off of your shipping journey if you're trying to get from Asia to Europe or vice versa. And so this is a route that is being used now by many cargo vessels and particularly oil tankers as well in the relocation and the delivery of fossil fuel, in particular liquid natural gas. And so this map is just showing how much activity occurred in the Arctic over that time period, 2009 to 2016. And it's really like quite amazing, because you would think that the Arctic, it's sort of this harsh area, remote, nobody ever goes there. Well, that's not true. I mean, this map is showing over 10,000 visits in some cases. Now, of course, this is all types of shipping. So this includes research cruises, which would be the major ones here in the central Arctic. Those are mostly research vessels, okay? But also tourism, and as I mentioned, the cargo. So, but I think, you know, what I want to point out here is, again, getting into the headlines or why the region is in a spotlight right now. These cargo vessels, they're either have ice strengthened hulls, or they travel, they may be icebreakers, but most of the time they are ice strengthened and they actually travel with an icebreaker. So this is a situation where they're actually contracting icebreakers to transit across the Arctic ahead of them to break up the ice, and then the flotilla of cargo ships then follow that. And in the 2018, 2019, you know, there were, I don't know, between 16 and 26 million tons of cargo shipped. But according to the Maritime Executive, which is a newspaper for this particular industry, they say that the goal for this industry is to ship up to 80 million tons of cargo by 2024, which is just a few years from now. So we're going to see an increased spotlight on the Arctic. And of course, the reason I'm bringing this up is because this has broad implications, okay, for all aspects of the Arctic system, from the climate system and the local environment, of course, thinking about pollution and the change to the environment that's occurring, both in terms of the atmospheric change and oceanic change, but also impact on local residents. Their loss of a habitat and a structure that they use for sustainable hunting or transportation, but that then being replaced by commerce and tourism. And then, you know, the implications for national security, perhaps search and rescue, or potential accidents or environmental catastrophes, perhaps due to potential oil spills, for example. So there's a lot of reasons to be interested in this area. There's a huge space here for folks to get involved in looking at the Arctic. There's so many different things that are going to need attention over the next decades as activity in this region increases. And so I think what my role in this space is to provide sustained long-term observations, okay, of the sea ice cover. And we need to have those to understand variability, like the natural variability that occurs from year to year, you know, between seasons, but also the long-term trends. And why do we need to make those observations? Okay, well, we need to do that to improve our forecasts. Just like we make weather forecasts, we need to make forecasts of the sea ice. So that's one thing. And we also need to understand, you know, the forcing mechanisms. What are the actual processes that are changing the sea ice right now? And that's going to be fed into longer term climate models that can predict on longer length scales beyond a forecast that might be for a week or a month, but to predict what might happen in a decade or a century from now. And these are really required because we need to make timely decisions as citizens. But of course, those stakeholders, those living and working in the Arctic, also need this type of information. So that's the motivation for the work we do. And then just to say, sorry, excuse me. Sorry. Excuse me about that. So just to say kind of what are we actually trying to measure? Okay, so not just measuring sea ice per se, but we're actually measuring the processes that shape the ice cover and the properties of the ice cover. So this is a graph showing the major processes, thermodynamic processes. So basically the incoming shortwave radiation and then outgoing longwave radiation and how that affects the ice cover through growth and melt. And then dynamics, which is basically the movement of the ice. So the ice is under the forcing of the atmosphere through wind forcing and the ocean through currents, and then the effect that that has on the ice. So we're interested in understanding these processes and how they're changing over time, but we're also interested in measuring the properties. So my talk is actually going to really get into the details of how we measure things like ice flows individual ice floes floating in the ocean, the shape of these floes, the height, the surface roughness of these floes, the width of them, things like the height of pressure ridges in the ice, how tall are these pressure ridge sails, and then of course the thickness of the ice overall and how that's changing. So those are kind of the properties that I'm going to be talking about. And then this is just a quick slide about some of the observational tools that we use for monitoring the ice. Now, these are really just, this is a very brief list. It's not all of the tools, but these are the tools that I tend to use in my research and my research team use. And today, I'm really only focusing on altimetry, which is from satellites, and an altimeter simply measures the time that it takes for a pulse of electromagnetic radiation to travel from the satellite to the Earth's surface and bounce off the surface and back to the detector on the satellite. So I'm going to talk about measurements from a range of different altimeters on different satellites. I'm not really going to get into the technical aspects of those altimeters, just to say that they're a combination of laser altimeters and radar altimeters. Okay, so for those of you interested in that type of thing. But yeah, so there's a range of different measurements and tools that we can leverage to understand sea ice processes and properties. All right, so just to kind of go back a little bit, when I started my own PhD back in the early 2000s, this paper was published by a colleague of mine, Greg Holloway, and his collaborator, Tessa Sue. And my advisor got kind of excited about this and was like, oh, this is really what we need to care about. We knew at that point that ice was already in decline. And we knew that from the passive microwave sensors that had been operating since the late 70s. So the measurements that I have been talking about up to now. But what we really didn't know was how thick was the ice. And in fact, was the ice actually thinning? Or was it thickening even in some areas? So it was this concept of measuring the sea ice in 3 dimensions, not just looking at the aerial coverage, but what is the thickness, and then using that to understand the volume, okay, the overall amount of ice we have. And so what Holloway and Sue were saying here is that, there were indications that, yes, the ice was thinning and thinning rapidly. And those observations were made from submarines. But their argument was, in fact, that the submarine tracks were sampling a particular area of the Arctic. And their point was that unless you had coverage across the entire Arctic, you could not actually tell really what was happening. So this set us up to propose to use satellite altimeters to measure the entire Arctic ice cover. Okay, and not just rely on submarines that were able to transit certain areas underneath the ice, or in fact, rely on humans to go to the Arctic and make in situ measurements, which of course they had been doing for many decades. So this was kind of the start of it. So just to kind of focus on those first of all, those submarine measurements, where were they? So there were submarine thickness measurements made right from the 1940s and 50s through to the 90s. They still are made, but very rarely now do we get access to these data. But the data that were made publicly available were in the so-called Gore box, named after Al Gore, our vice president. So potentially, sort of strange kind of naming, but it was really to do with the fact that this was international waters. And so these submarines, of course, are transiting everywhere. I'm sure the measurements are in all parts of the Arctic, but the only measurements that as civilian scientists we were able to look at were these measurements in the central Arctic. And of course, it gave us an indication that there was a broad range of thicknesses. I'm sorry, the scale is cut off the thickness bar here. I'm just wondering, yeah, okay, there it is on the next slide. So we're looking at the blue here is around 1 meter of thickness, and then the reds and light red and white is about 5 meters, okay? So we can see, just by looking at these early measurements, the submarine measurements, okay, a very broad range from 1 to 5 meters in thickness, but kind of limited. And again, what Greg Holloway was saying is this is not really sufficient to understand whether the ice is thickening or thinning at this point. And at this point, the data that I'm showing here had been used and published to suggest the ice was thinning. So back in, turning back our attention to satellite altimetry, we had the first measurements of ice thickness were derived from some satellite radar altimeters on European ERS 1 and 2 satellites. And this was actually work of my own advisor back in London, Dr. Seymour Laxon, and he published this in 2003, just a couple of years after that Holloway and Sue paper had been published. And, you know, it showed, wow, like there's really a gradient in the ice thickness in the Arctic. It indicated, you know, the thickest ice was somewhat restricted to this area around Greenland and north of Canada. And then as you transitioned across the Arctic to the Siberian side, you actually could find areas of much thinner sea ice. So this is kind of the first exploration or first demonstration that we could measure the thickness of the ice from space. The problem here was that it improved the spatial information beyond what we had from the submarines, right? But it also like left still a gap north of 81.5 degrees. And that was simply because these particular satellites were not designed to measure the polar regions. These were environmental satellites that were launched by the European Space Agency. So they had multiple instruments on them, and no one really thought about using them to look at the polar regions. So it was kind of beyond the scope of the mission requirements. So anyway, moving forward, because of the success of that radar altimetry demonstration, NASA then became interested in doing this. And in 2003, NASA launched the ISAT laser altimeter system. And the ISAT system actually was the first altimeter dedicated to polar measurements. Okay, so the entire mission was dedicated towards measuring the changes in ice in the Greenland and Antarctic ice sheets primarily. And then kind of a secondary idea was looking at changes in the sea ice cover of the polar regions. But the reason I'm showing this is that we obtained kind of a more complete picture of the ice thickness. Now, I should have mentioned that these measurements I'm showing you are for the end of winter. So these are all to do with the thickest ice at that when we reach our ice maximum in March and April. Okay. Now the advantage of ISAT-2 was that we got this like kind of complete picture across the Arctic from what we had with the ERS 1 and 2. We could fill in that gap towards the North Pole, but the satellite had some instrument issues. And so we were only able to get seasonal sampling. And so we only made this measurement in winter, more or less, each year for, I think in total, we made 6 years of measurements. So 6 winters, basically, of measurements, I believe. So it was an advance, but not really sufficient. And then we had go back to the European Space Agency. They then launched their next radar altimeter, Cryosat-2. And this is really now the workhorse for looking at changes in ice thickness in the Arctic. So Cryosat-2 was launched in 2010 and continues to operate today. And it's, as I said, a radar altimeter. And Cryosat-2 is providing us with complete spatial and temporal coverage of the winter time. Okay, so it spans, the measurements of thickness span from October through to April or May of each year. We don't obtain any information about the thickness of the ice in summer. And that is because the radar has specific issues that it can't actually determine the difference between leads in the ice cover, the cracks in the ice cover, and melt on the surface of the sea ice. So that restricts our ability to measure the thickness in summer. But overall, you can see this picture that was built up over time. I'll just kind of go back through that, of this sort of gradient in ice thickness from the multi-year ice, you know, where we saw that old ice is in fact the thickest ice north of Greenland and Canada, across the gradient diminishing across then towards the Siberian side, where you have the seasonal sea ice cover that comes and goes each year. And if you believe these measurements and you think, okay, there's no biases between these satellite instruments, which is probably not true, you can see that there was a drop in thickness of about 60 centimeters over this 24-year period of satellite altimetry. Whoops, sorry. Oh my gosh, sorry. And so that's actually 60 centimeters is actually about 20% of the total thickness, right? So if you think that on average the ice is maybe about 3 meters thick, So that's a pretty big change in that time period. But as I said, I mean, that's if you really trust these measurements and believe there aren't any biases in them. Okay, so I'll just leave it at that. So now that brings me on to ISAT-2. So we launched ISAT, so we're back to NASA again. So you can see there's like the seesaw between the European Space Agency and NASA. And so we're really strong collaborators. Each group collaborates with each other very closely. We talk to each other every week. So now we're back to the NASA side this time when we launched ISAT-2 in 2018. And I'm a member of the ISAT-2 science team. So I'm really privileged to talk to you about this mission, and just want to explain for the last few minutes of the presentation, the last 15 minutes, to really kind of go into what types of measurements we're getting from ISAT-2. So it's another laser altimeter system, okay, and it's operating in the green wavelength, right? So 532 nanometers. So it's sending out literally green laser pulses from the satellite 500 kilometers above the Earth's surface, beaming down onto the Earth. We're measuring very precisely the time it takes for that laser pulse to hit the surface and return to the telescope on the satellite. And because we know the speed of light and we know that time, we can work out the distance, right? So then we also know the height of the satellite above the center of the Earth. And if we subtract those two measurements, we get the height of the topography of the Earth relative to the center of the Earth. And we then can apply some references to that, reference surfaces such as the reference ellipsoid or the geoid or the mean sea surface, to understand the height of particular features on the Earth's surface. So the mission is all about measuring topography, Earth's topography, and it's operating over every surface. I'm only going to talk about its capabilities over sea ice, but it's measuring the land, it's measuring the height of lakes, trees, tree cover, it's measuring changes in the glaciers on Earth and changes in the ice sheets that cover Greenland and Antarctica. So the important things to say here are that we have a very high resolution measurement. The footprint on the surface is about 12 meters, but it is oversampled. The pulse repetition frequency is 10 kilohertz. So basically we're obtaining a sample every 70 centimeters along track. And the pulse is split into 6 beams. It's one laser, but it's diverted into 6 beams. And each beam is paired. So we've got basically 3 pairs of beams. A weak beam and a strong beam are paired together. We set that up for particular reasons I don't really want to go into. We're not actually really using the weak beam information right now. It's fine, like there's nothing wrong with it, but the information that we're getting from the strong beams is sufficient really to do the science that I'm going to show you now. So if you want to learn more about ISAT-2, just go to the webpage that I've listed there at the bottom of the slide. And what I want to talk about now is how we can actually, the reason I want to talk about ISAT-2 is that it is a game changer for measuring sea ice. So this is just a cartoon. And it's supposed to show, it's probably a really bad cartoon. I'm not very good at art, but it's just the evolution of the ice over time, okay? So as I mentioned, we start off with full freeze up in, say, October, and then we go into the polar night, and then we go into we reach the maximum sea ice volume at the end of winter. The sun starts to rise, and then we get melt onset. Okay, so the sea ice starts to melt. Basically, the snow on top of the ice starts to pool in these ponds, melt ponds. And then by the end of summer, we're left with just discrete ice floes floating in the Arctic Ocean. And these are the floes that have survived the melt process and continue on into the second year. So this ice then becomes multi-year ice. So this was just an excuse to show you loads of really fun photographs of sea ice, basically, from my colleagues. So ISAT-2 is actually capable of making measurements in all of these time periods. So the excitement for me is that we're actually able to look at processes throughout the year. And it's the first time we've been able to do this with a satellite altimeter. So that's kind of the advance that ISAT-2 provides us with. So I mentioned we launched in September of 2018, and this is the first data that I got my hands on in October of 2018. So if you remember from the previous slide, October is just when the ice is starting to refreeze. The ocean is freezing over essentially. So what I'm showing here on the left-hand side is a SAR image, okay, synthetic aperture radar from Sentinel-1. And it's just showing it's basically a radar picture of the sea ice surface in the Beaufort Sea. And so the gray and white areas are ice floes. These are this is the multi-year ice that survived the summer and is carrying on through to the next winter. And then the dark areas are regions of the open ocean that are freezing over. And you can kind of see in the SAR image, there's some structure in that indicates that this is actually ice that's freezing in the ocean as opposed to just being open water. And then I have my ISAT-2 tracks that cross through this image and spatially and temporally coincident. And I'm showing what they look like over here on the right-hand side. So the graphs on the right-hand side are the topography of the surface, okay? So this is the topography of the sea ice surface from the 3 strong beams on ISAT-2. And like, as I said, this was the first data that I obtained as a science team member, and it was just so exciting to see the detail in the topography, how much the topography changes, and immediately you can identify things that are going on. So you can see this rough sea ice flow that's pretty thick here. This is just the expression of the topography of the ice above the local sea level. Obviously, there's a whole chunk of sea ice below the water level that we're not measuring. This is just the freeboard, if you like, so that the surface expression or the height of it above the local sea surface. So you can see how rough the ice is. You can see these pressure ridges, these really thick areas of sea ice, and then areas of really flat topography where you have, this is a lead, basically the area of, you know, the open ocean essentially, okay, and just how flat that is as it's refreezing. So it's really exciting. Like, okay, this is going to be great. I mean, this data is fantastic. And I should just say that the gray dots in the background are the full sampling, that full resolution that I mentioned earlier of measurements every 70 centimeters. And then the solid lines in these curves are like the red and blue and green. That was just a, I can't remember, a modal filter that I applied to the data just to kind of give you an indication of the average surface there. So we use this anyway to make a measurement of sea ice freeboard. So just the expression, as I said, of the ice above the local sea level. So the graph here, the third one from the left, is the sea ice freeboard from ISAT-2. And this graph is showing, this slide is showing just, you know, in context, how does ISAT-2 stack up with other and independent estimates? So I've already introduced you to Cryosat-2, which is still operating, and that's a radar altimeter. So you can see the Cryosat-2 instrument is also providing us with a freeboard estimate. And these are very, very commensurate with each other. There's a really strong correlation between these two freeboard estimates, but what you're going to notice is that the magnitude of the freeboard is different. And that's because Cryosat-2 is a radar altimeter, and the wavelength that it's operating in is roughly 13.5 gigahertz. It's a Ku band radar. That radar energy can penetrate through the snow cover on the sea ice surface. So the freeboard here is really the ice freeboard. Whereas the laser altimeter on ISAT-2 is actually bouncing off of the snow surface. You're not getting very much penetration of the green light into the snow cover. So the freeboard from ISAT-2 is actually both sea ice plus the overlying snow on top. So if you difference those two freeboards, that's going to give you an indication of how thick the snow cover is on the sea ice. So that's another cool measurement we're making that I actually didn't show here. And then on the left-hand side, it's actually just a different type of radar instrument. It's called ASCAT, which is a scatterometer. And that's just giving us an indication of backscatter from the sea ice surface. And the differences in backscatter can be used to identify the older multi-year sea ice versus the seasonal sea ice. And so if you kind of combine this information, you can work out the distribution of freeboard for multi-year ice and the distribution for the seasonal sea ice. So just to sort of show you that in December, you know, sort of middle of winter, we're making these really nice extensive measurements of the Arctic Ocean and the ice cover. And then just to kind of go into the detail, because I mentioned how high resolution the measurement is, I just wanted to show you kind of individual features that we can measure on the ice surface. So again, these are ISAT tracks. These two graphs in the middle are surface elevation, okay? And it's, again, the topography of the sea ice. Now, this is really zoomed in. These are just 2 kilometers. This one is 2 kilometers and this one's 1 kilometer on the right-hand side. And what we're showing here is how ISAT-2 is tracking the topography of the surface. And each of these kind of modes in this graph, each of the points at which the topography spikes up is actually a pressure ridge on the surface. So what we did here is we actually used an aircraft to underfly the satellite and obtain spatially and temporally coincident data. And we could identify these pressure ridges in the aircraft LiDAR, okay, the laser altimeter in the aircraft, and also photographs. Okay, so here on the right-hand side, you could just see this basically just an optical image, a camera, basic camera on the aircraft showing you what the ice surface is like. So then these numbers here indicate these pressure ridges that we're picking up in ISAT-2 data above in the graph above. And then the details here, I'm not going to go into too much. We're just comparing different algorithms that we're using to track the surface with, you know, applying algorithms to the ISAT, to the raw ISAT-2 data to obtain surface topography. And then, as I said, validate it against the aircraft, which is the green curve here. So basically just validating the satellite with the aircraft. We just published recently a paper that sort of covers all of the results I'm showing here. It just came out this week on Monday. So if anybody does want to know the details here, I'm just kind of covering it quickly. I just in order to get through the presentation in a timely manner. But if you do have questions or interest, definitely check out the paper because you'll get more details there. And then just to mention the thickness, as I said at the very beginning, our interest is in looking at how thickness is changing over time. And so now we have kind of 2 winters of thickness from thickness measurements from ISAT-2. And I just for comparison, I'm showing CryoSat-2. So this is the radar instrument on the European satellite. And then on the left is the laser instrument on NASA ISAT-2. And again, really, I don't know, satisfying that these maps are very well correlated with each other. And that's proven if you look at the distribution here. So on the right-hand side, I'm showing the thickness distribution now. And what I wanted to point out here is that the thickness of the ice is ranging, of course, from 0 to 5 meters, as we said, right, you know, a few slides ago. But what you can see is that there's a mode in the ice thickness around 2 meters. And in fact, if you kind of compare the 2019 distribution with the 2020 distribution, you can see that in 2019, there was actually a bimodal distribution. There was this second mode at around 3 meters. And that actually is associated with the multi-year ice, the older, thicker ice. And then the main mode is kind of the average of the, you know, it's mainly seasonal sea ice, but influenced a little bit by the multi-year ice. Okay, but that secondary mode kind of disappeared in 2019. In 2020. So we went from this mode in 2019 around 3 meters to sort of no longer being a mode in 2019. You can see that there's data there still. There is ice at 3 meters, but a little bit less in terms of the coverage. And if you look at the maps, then you can kind of see what happened, and it's really this thick area of multi-year ice that diminished or was lost in between the winters of 2019 and 2020. So this is kind of to go along with the graph I showed at the very beginning, where I said ice extent in 2020, in April 2020, was a record low, you know, maybe 3rd or 4th on record. The ice thickness was pretty low this year as well. So we're kind of looking into this, more work to come on this basically in the next few months. So moving along into the summer, I've only got a couple of minutes left. I know I asked for a 10-minute warning. I think I've blown through that, right? But I'm going to keep going here for a couple more minutes and then I'll be concluding. So I think we're okay on time. So then, yeah, so the summer, this is kind of exciting. This is work my graduate student, Ellen Buckley, is doing. And this is just a satellite image, an optical image of the sea ice surface. Okay, so if you look at the map on the right, top right, it's just showing an area off of Greenland. northern Greenland, and it's actually called an area called the Lincoln Sea. And the optical image, this is actually a MODIS, I think, MODIS image here that I'm showing. And it's just showing you like everything basically that the satellite sees. So like there's cloud here, then there's kind of this blue surface, which is actually the sea ice, but undergoing melt. So there's meltwater on the surface, and that's why it's tinged blue. And then you can see the exposed rock of Greenland, and then the Greenland ice sheet down here at this bottom part of the image. So if we zoom right into this region in the Lincoln Sea, this is a kind of crazy graph. This is this slide is just a summary slide of Ellen's work, Ellen Buckley. So there's a lot to take in here, but on the right hand side, if you look at that first, this is a high resolution image of the sea ice surface, okay, and that's zoomed in area right in the Lincoln Sea. So it says here Sentinel-2, okay, so the 22nd of June 2019. So Sentinel-2, we're using the MSI instrument, multispectral instrument on Sentinel-2, which provides imagery at different bands, different wavelengths, but this, we're just showing the optical imagery here. So the visible wavelengths, I should say. And then overlaid on that are all these green tracks. Okay, so the green tracks are the ISAT-2 tracks, the ISAT-2 orbits across the surface. And I forget exactly what the time difference between these is, but it's a roughly 30 minutes that we were able to obtain ISAT-2 and Sentinel-2 data within about 30 minutes of each other. And what was cool about this is that we were able to like find individual melt ponds in the Sentinel-2 data and check out what that signal looked like with ISAT-2. So these are melt ponds 7, 8, 9, and 10, which are zoomed in here. So the Sentinel-2 imagery has a resolution of 10 meters. Each pixel is 10 meters by 10 meters. So you kind of see these blurry images of little melt ponds on the sea ice surface. And then if you go over here on the left-hand side, you're now looking again at elevation or topography from ISAT-2. So similar to the measurements we've already looked at in winter, right? But now you can see the sea ice surface is really flat. And what we're pointing at here are these ponds that are occurring on the surface. And these are the melt ponds. Now, these are really quite big, deep melt ponds on the ice surface. And we were able to use ISAT-2 to track the topography or the bathymetry, if you like, of these ponds. The green laser is actually able to penetrate the water in these ponds, and we're able to track the bathymetry of the pond and therefore estimate the depth of these ponds. So the graph on the bottom right is then providing you with an estimate of melt pond depth for the melt ponds in this area of pretty thick multi-year sea ice. So the depths, you know, the modal depth was I think about 35 centimeters, but the range was anything from 10 centimeters up to 2 meters. And I think the average was around 80 centimeters, if I remember correctly. So new capability, we've never been able to measure the depth of ponds from space before. It's been demonstrated with airborne instruments, but not with satellites. So it's kind of a first for ISAT-2. And then I think I might just skip over this one briefly. This is again just showing September 2019. I've already shown October, but it's a similar situation where you've got distinct ice flows. And then this again is just a Sentinel-2 image with the ISAT-2 tracks overlaid on it. And this is by another graduate student, Rohan Lee, in the Geographical Sciences Department at the University of Maryland. And on the bottom here, you can just see this is the topography or elevation from the ISAT-2 laser beams, the 3 strong laser beams. That just kind of zoom in on this really quickly. It's just kind of phenomenal to see this, but so again, we're overlaying coincident data from ISAT-2 and Sentinel-2, and now we're able to really look at individual ice flows and look at not only the topography of that ice flow, we're looking, you know, we can see the width of these ice flows, and from this we can actually estimate not only the freeboard of this ice flow, but if we make some assumptions about the snow cover being quite limited on this ice flow, since we're in September, that most of the snow is melted at this point, we can work out the thickness of these ice flows. And this particular flow that I'm pointing at, the one in the center of the image, was really quite thick. I think it was over, well, it was definitely over 5 meters. I want to say it was the maximum thickness of this ice flow, I estimated to be about 9 meters thick. So really huge ice, chunks of ice basically left. They're kind of, they look small, but they're really big. And then just to kind of highlight the level of detail, these little ice flows down here in the ISAT-2 data, which again, you can actually see in the Sentinel-2 image, these ice flows are only like 20 meters wide in some cases. So really high resolution. So from all of that, we can make a whole range of measurements. We can look at the height of the sea surface in the leads and the cracks in the ocean. The cracks in the sea ice cover. We can measure the height of pressure ridge sails, as I said. So these pressure ridges in the sea ice cover, we can look at the height of those and compare pressure ridge sails between these different ice types, the seasonal ice and the multi-year ice. We can look at the width of these leads between the ice flows, and we can look at the size of flows. Now, this is just a kind of graph to summarize all of these parameters that we're capable now of measuring with ISAT-2. But the bottom line here is that these types of high resolution measurements are really required now for the next generation of sea ice models. So as we move forward with predicting, well, with forecasting sea ice, but then predicting it on longer climate scales, we really need information about things like how big the flow sizes are, what sort of lead width is occurring in the Arctic and how it's changing over time, because this is going to tell us about the air, ice, ocean interactions. Okay, so how much ocean interactions you have with the atmosphere. So in the case of a lead, that's where you get a huge heat flux from the ocean into the atmosphere, for example, in winter. So yeah, that just brings me to conclude basically that we're in a kind of golden era for polar satellite altimetry. We have 2 altimeters orbiting right now using different types of radar, different types of satellite altimeters. So we can kind of compare these observations, look at sensor bias, look at how the different wavelengths interact with the sea ice, which is very technical, but really interesting and is a huge area of research for myself and my colleagues. So like looking at the penetration of that radar energy into the snow cover. And then just to say that ISAT-2 is delivering really the highest resolution measurements we've ever made from space in terms of ice topography. And this is allowing us to make measurements of a whole range of parameters, a whole range of properties of the sea ice cover, including the height of pressure ridges, the frequency of those ridges along the surface of the ice, the distance between the pressure ridges, the depth of melt ponds on Arctic sea ice, and you know, all from a distance of 500 kilometers. And I didn't mention this, but the precision of the measurement is 1 centimeter. So it's like mind-boggling. So yeah, we're just excited about this instrument, excited to, you know, produce these measurements and hopefully, you know, generate some data sets that we can kind of share with the public beyond just the mission requirement, which was to measure freeboard. The instrument was designed to measure freeboard and thickness. We're going to have all these additional pieces of information about the sea ice cover. So we're also looking forward to results from Mosaic. I know that there's folks in the group who are heavily involved in Mosaic, which was an in situ, you know, field campaign that's just concluded after a year, basically on a research vessel frozen into the sea ice. So we're really kind of excited to compare the field measurements with the ISAT-2 measurements that we're getting. And if folks are interested in accessing any of this data, I've just put some links here at the bottom of the slide. So, you know, go ahead and explore. And yeah, if you've got an interest or you're kind of keen to look more at this, don't hesitate to contact me. Always looking for people to come and join our group as well. So if this is something that really gets you excited, yeah, don't hesitate to reach out and you know, we can give you some information about opportunities coming up. So thanks again for having me. I have a few minutes left for questions, not too many, but yeah, it's a pleasure speaking to you today about ISAT-2. Thanks again.